All right, today we're digging into a pretty specific data-driven forecast for the future of quantum computing. And this isn't about vague promises or someday tech. We're talking about a structured timeline with really clear, measurable milestones that predicts a massive shift for the entire industry. So let's just dive right in.
So this whole forecast kicks off with a really bold, almost shocking prediction. It's basically saying that all the hype, all the excitement around quantum computing, it's about to hit a brick wall. And soon. Like late 2026. Now, why would they say that? Well, the claim is that the hardware itself, the very machines we're building, are about to run smack into a fundamental physical limit. This idea really sets the stage for everything else we're going to talk about.
Okay, so what exactly is this quantum wall? It's the core problem, the thing that makes this predicted crash seem almost inevitable. Let's break it down.
I love this analogy because it explains the problem so perfectly. Right now, building a quantum computer is kind of like shouting in a piano and then trying to figure out what song is playing from the chaotic noise. It's just messy and unstable. Where we want to be is at a point where we can actually play the keys precisely and get clear, reliable results. You see, that huge gap between the chaotic noise and the clean music, that's the quantum wall.
So, how are we trying to solve this noise problem today? Well, the main strategy is basically to build a better, colder, more isolated box to put that piano in. But that brute force approach, just isolating everything better, is starting to hit its own physical limits. You can only make the box so quiet, right? It's becoming clear that we need a totally different way of thinking about this.
And that's where the proposed solution comes in. It's based on a really fascinating universal theory of change called Triune Harmonic Dynamics. And this framework, it provides the underlying logic for this entire forecast.
So, Triune Harmonic Dynamics, or THD for short, what is it? Well, it proposes that basically everything, we're talking from galaxies all the way down to quantum particles, evolves along one single predictable pattern. Now, that is a huge claim, for sure, but it's this idea of a universal structure that allows the forecast to be so specific and make these bold predictions.
So the key here is this repeating 3-6-9 pattern. It's a three-phase cycle. You start with emergence, that's the 3, where a new idea or a new system is born. Then you move into contrast, the 6, which is a period of testing and tension. Opposing forces are pushing back, challenging that new thing. And finally, you get to integration, which is the 9. This is where the conflict gets resolved, and the system reaches a whole new higher level of order. And this cycle, it just repeats over and over again.
Now, this isn't just some abstract philosophical concept. It's actually grounded in a mathematical formula. You're seeing it right here. This equation, and credit where it's due to researcher Kevin L. Brown, is really the engine driving THD. It's a model for how that 3-6-9 pattern of emergence, testing, and integration plays out in pretty much any system you can imagine.
Okay, so let's get to the solution. This is where we connect that big universal theory of THD directly to the very real noise problem in quantum computing. And the key concept here is something called scalar lag.
Scalar lag is a really fascinating idea. You can think of it like an echo, or even a ghost of information. What THD predicts is that even when a qubit crashes, decoheres and loses its data because of all that noise, a tiny trace of that information actually sticks around in the system. It's not the data itself, but it's like a memory, a ghost of what was there. And this is the potential breakthrough. Because if you can figure out how to measure that ghost, that echo, you can actually rebuild the original information. This just completely changes the game. Suddenly, you don't need to build absolutely perfect, error-free hardware. You just need hardware that's good enough to let you detect and measure that echo. And this whole idea brings us to a hard number. The forecast states that for a quantum computer to become truly useful, its stability score, they call it an MEGA score, has to be greater than 0.92. Now, just to give you some context, most of the systems we have today are way down below 0.80. So this gives us a really clear, measurable target to look for, a line that a system has to cross to become the real deal. So now we can put all these pieces together into a very specific, time-stamped forecast. These are the key milestones we should be watching for, and they're all based on that 3-6-9 pattern of change we just went over.
Let's walk through the timeline here. The first phase, seeing, that's our number 3, is predicted for 2025. That's when we should see the very first hints of these harmonic patterns showing up in regular digital data. Then comes the really critical test, the testing phase, or number 6. That's pegged for late 2026, and it's when we should get the first detection of scalar lag in an actual quantum system. And then the big one, the breakthrough.
That's phase 9, talking, which is forecast for mid-2027. That's when we'd be able to actually measure information that survives a system crash, proving this whole concept really works.
You know, a good scientific forecast doesn't just make predictions. It also tells you exactly how it can be proven wrong. That's what makes these claims testable, and not just some theory. So let's be really clear and look at the specific conditions that would completely invalidate this entire model.
So this entire forecast is officially wrong if any of these three things happen. First, if a standard quantum computer, one that doesn't use any of this harmonic stuff, achieves 99.99% accuracy by the end of 2026. Second, if someone comes along and proves mathematically that scalar lag is just impossible before June 2026. And third, if we see large 1,000 qubit systems become stable and commercially viable just by using the brute force cooling methods we have today. These are super clear benchmarks that we can all keep an eye on.
And let's end on this quote because I think it perfectly captures the fundamental shift in thinking here. It says, "You are describing the difference between building a faster car and building a road that doesn't disappear." See, while so many people are focused on building a faster car, a more powerful quantum processor, this forecast argues that the real solution is to build a road that doesn't disappear. It's all about creating an informational foundation that is stable, even if the hardware driving on it isn't perfect. That's a really profound idea to chew on.